Hello everybody, I'm going to solve two types of problems in this video. One sketching as simple surfaces in R3, another one's related with the partial differentiation. In this question, we will first sketch some level curves and then YZ profile. By using these two, we will sketch the surfaces. So the level curves gives us the projection onto the XY plane, and then the YZ profile will give us a view or a projection for the YZ plane. Then by thinking of these two cases, we try to visualize the surface in three-dimensional space. That's the idea for this question. In your question set, we have several surfaces. I'm going to solve for this question for C part and E part. Okay, level curves. So we have the surface z square is equal to x squared plus y squared minus 1. We put the sum values for z and we look at the curves occurring in the xy plane. For z is equal to 0, we obtain a circle with radius 1. That will be this circle. For z is minus plus 1, we have circle with radius root 2, which will be the blue circle here. Then for radius, for the z is equal to minus plus 2, we have a circle with radius root 5. That's the green one. For minus plus 3, the level curve will be the circle with radius root 10, which will be the dead circle. So this is the projection in XY plane. Then the next task that we need to do, look at the YZ profile, which means how we are going to obtain. We will put the x is equal to 0, and we will look at the projection of the surface on the YZ plane. If you put x is equal to 0 in the equation, we have y squared minus z squared is equal to 1. This is a hyperbola equation. Then on YZ plane, we will have this hyperbola. Now, looking at this hyperbola and those level surfaces, we will just sketch the surface in three-dimensional space. This is not a graphing. Graphing of the surface is much more complicated. Now we are just trying to sketch, just try to visualize what kind of surfaces we have. So the YZ plane, we have a hyperbola, and we have circles on here. When we project those circles on the XY plane, it will look like the level curves that we obtain like this here. And yeah, the surface will be, I think it is easy to visualize for this surface. That's how this look like. But it is not the case for complicated surfaces. For the next question, we have a bit more complicated surface. Z is equal to x squared minus y squared. To visualize the hardness, the difficulty here arising from the just visualization part. Let's have a look how we do. Z, by just giving the values to z, we obtain the level curves. For z is equal to 0, we have x squared minus y squared is equal to 0. We can write this polynomial is x minus y, x plus y. So x minus y is equal to 0. It will give us a line, x is equal to y, which is that line. And x plus y is equal to 0 will give us a x is equal to minus y, which is that line. For z is equal to 1, we will have a hyperbola, x squared minus y squared is equal to minus 1. That's orange color that I used. That's the z is equal to minus 1 hyperbola. For z is equal to 1, we have the hyperbola, this one. For z is equal to minus 2, we have hyperbola, the purple one. And so last one is x squared minus y squared is equal to 2. We will have this hyperbola over this side. Now, these are the level curves on XY plane. That's a projection of the surface on XY plane. And the YZ profile, and to obtain the YZ profile, we put the y is equal to x is equal to 0. It will give us the z is equal to minus y squared. That will be the parabola in the sky. If it says z is equal to y squared, it will be this shape. And the opposite of this will be z is equal to minus y squared, which is that one. So by thinking of this in the YZ appearance and thinking of this one on the XY appearances, and try to think that what kind of surfaces may give this kind of projections is the challenge for this question. So here we have this curve. This hyperbola will appear here, and we have dot 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 sections in there, and we have this kind of hyperbolas. When we projected that one, it will give us this kind of level curves. And this shape, the surface is called the hyperbolic paraboloid saddle. I just didn't like very much about my drawing, so I added a nice, a proper graph by using the MATLAB. So this is from the, Mathematica. This is from the Mathematica graphing, just to help you to visualize the hyperbolic paraboloid. This is just a graphing, just to visualize by using the XY plane projection and YZ projection, figuring out and sketching that just the surfaces. It's just a simple sketching. So don't expect too much. If you want to do the graphing, it will be much more complicated and more work needs to be done. In that level, that's enough. Next question about the partial differentiation. So we have this function, and we would like to calculate this partial differentiations. The key is when we are differentiated, for example, with respect to x of this function, we assume the y as a constant. So if we treat y as a constant and differentiate with respect to x, we have ex squared some constant, right? Then the derivation of that will be, the constant will be here, will be in front of the function, that's y. And then you have ex squared y, but x squared is also a function of x squared. We need to think about the derivation of x squared as a chain rule. So that's the derivation of x squared is 2x. Altogether is 2xy ex squared y. Next, we want to derive this function with respect to y. So we will assume that x is a constant. So the function is some constant y, right? The constant will be in the beginning of the exponential function. Then we have exponential x squared y. So that will be the differentiation with respect to y. Now, if you want to differentiate with respect to dy dx, so dy is in first, and then here we apply to dz dx. dz dx we calculated 2xy ex squared y. Substitute in. Now we want to differentiate this with respect to y. So we will treat x as a constant. We have y here and we have y here. So this is like a product of the two functions in y. So we need to apply the product rule. So this is 2x, derivative of this, just 1. Altogether we have 2x ex squared y. And then the derivation of this times the derivative of this. We have 2xy, and the derivation of this with respect to y will be x squared exponential x squared y. That will be 2x y x squared, that will be 2x cubed, and then the exponential x squared y. I think it is straightforward. Now the next question, that is the third problem sheet in your that's the third problem in your sheet. First of all, we want to find out the first partial derivatives and then the second partial derivatives, all of them. And then we want to verify the second partial derivatives dy dx is equal to dx dy, that one. I'm going to solve for this question for question B. Just in this moment, I would like to remind you one important fact. That is in your lecture notes. It's given theorem 128. That's a mixed derivative theorem. This partial derivatives with dy dx dx dy, this one here, this equality here is not, it may not be the case in general. When is this true? If we have a function in two variables over the real numbers, and if all first and second partial derivatives are continuous, then we have this equality. Otherwise, this equality is not satisfied in general. So I just would like to remind you about this fact. I would like to recall the derivation of the tangent inverse x. Just reminding ourselves that this derivation is 1 over x squared plus 1. Now let's try to find out all first and second derivatives of this function. Okay, let's say, in order to be able to do it step by step, let's say u is equal to y over x. So dz over dx. So we want to, it's basically the chain rule. So we want to differentiate z with respect to u, and then the u with respect to x. So the dz with respect to u, it's just 1 over 1 plus u squared. This with respect to x, the u with respect to x. So the y is a constant. It's just a constant. It will be here. And we have d x inverse x, differentiation of x minus 1 with respect to x will be minus x squared. Right? And if you put the u back in, we have y over x squared here. So if we simplify this expression, we have x squared plus y squared divided by x squared. That is x squared in the denominator. Denominator will cancel out with the x minus 2 in here. Then we have minus y x squared plus y squared. Now let's calculate the derivation of a z function with respect to y. Dz du du dy. So the derivation of tangent inverse u, 1 over 1 plus u squared. This with respect to y is just 1 over x, because the x is a constant. So that will be just a 1 over x, because the derivation of y is 1. Then we have simplified, putting the u back in. We have x squared plus y squared divided by x squared. That x squared in that denominator over here would simplify with this x here. Then that x there will be on the, will come back into the denominator. We'll go back to the denominator, and then we will have x squared plus y squared. So these are the first partial derivatives of this function. Let's have a look at the second partial derivatives. This is dx dy. So that's dx. We will put the dz dy in here. Dz dy is x over x squared plus y squared. That's what we calculated. Put it in. Now think of this as u and v, like a quotient. That's u is equal to x. Let's think about u is equal to x, v is equal to x squared plus 1, and apply the quotient rule. So v and then derivative of u minus u derivative of v divided by v squared. That's the quotient rule. Now we are doing everything with respect to x, so that we have the x's there. So v will be x squared plus y squared minus, so du dx will be 1, minus u will be just x. V with respect to x will be 2x. Simplifying, divide by v squared, which is x squared plus y squared squared. Simplifying this expression, x squared plus y squared minus 2x squared will give us a minus x squared, and we have a y squared here, divided by x squared plus y squared, y squared. Next one, d squared z dy dz. So dy will be here. We plugged in dz dx. We calculated here previously. So that's dz dx minus y x squared plus y. Plugged it in. And now we differentiate everything with respect to y. Again, we apply the quotient rule. If you don't have to write it down this section in your answer, if you're doing it with your mind directly to this section, you can really omit this part when you're solving this question. I just wanted to step by step to make it clear for everyone. But if you're happy with doing it with your mind, if you're quick, that's perfectly fine. You don't need to add this part in your answer. Okay, here the v x squared plus y squared, the derivation of u with respect to y is just minus 1. Then u is minus y, which is that guy. And then we are taking the derivative of v with respect to y is just 2y. And then you divide by v squared is x squared plus y squared squared. Simplifying this numerator will give us minus x squared, and then you have a minus y squared here, but we have plus 2y squared there, then we have y squared there. As we see, these two expressions are the same, so that's what we wanted to verify in some stage of this question ask. What are the other partial derivatives? The other partial derivative d squared, we differentiate with respect to x twice, and we differentiate with respect to y twice. Dz over dx, so this is the dz over dx, and then we differentiate again with respect to x. Y here is the constant, because we are doing the partial derivation with respect to x. You can think of that one in two different ways, right? We can do this by using the quotient rule, or we can do this by using the chain rule. So I'm going to do that by using the chain rule here, and for this part I'm going to use the quotient rule, just to make it clear. I mean, doing solutions in two different ways may be helpful. So for example, we can think of that one like a 1 over u, and so d over u, 1 over u du dx. That's what we want to calculate. So I am doing like a function to function. So y minus y is a constant. It's there, stays there. So 1 over u derivation with respect to u will be minus 1 over u squared, and du with respect to x will be 2x. Now u squared is x squared plus y squared squared, and we have negative, that will be plus, so 2xy divided by x squared plus y squared squared. As one way of doing it, I will show it here by using the quotient rule, another way of doing that. So d squared z dy squared, dz over dy is x squared plus 1, as we calculated above, plugged it in, and again we are differentiating with respect to y. If you think of as a quotient rule, this times the derivation of this with respect to y is 0 times anything, we don't care, and minus x and the derivative of the denominator with respect to y, which is just 2y, and then divided by the whole denominator square. So that is the quotient rule. So what we have, minus 2xy x squared plus y squared square. So that's all I wanted to say for this part of the solutions, this part of the video. Thank you very much for listening. Thanks. Bye.